Hey there everybody, and welcome to the final video that covers material that you need for your Chapter 15 project. This video picks up where the last one left off. We left off by talking about what delegate bias is and how you might calculate it. In this video, I will show you an actual calculation for the delegate bias of candidate 3 under Hamilton's method. So recall that if you want to calculate an asymptotic delegate bias, you have to have a method in mind. So for this video, we will have Hamilton in mind. And you also have to have a candidate in mind. So I'll show you the calculation for candidate 3. The calculations I show you, though, can be fairly straightforwardly mimicked if you change the method to, say, SUQ or something, or if you change the candidate. So hopefully what I show you here is enough that you can mimic what I've done to move to a different method or to a different candidate. So with Hamilton's method in mind, how do you calculate the delegate bias of a given candidate, say candidate 3, under this method? Here's what we said in the previous video. I just outlined this, but I didn't do it. But here's the outline of what you do. You take a typical apportionment region for Hamilton, which, as we've seen, is a hexagon. You then put it in the floor, because recall that these hexagons are living in a slanted triangle that's slanting through 3 space. It was part of this plane that slants through 3 space. If you want to take a double integral, though, you must have a solid that's hovering over a region in 2 space. You must be hovering over something in the xy plane. So I have to take my hexagon, put it in the xy plane, then I can integrate deviation from quota over that region and then divide by the area of that hexagon to create an average value. So all this just to say that we're going to calculate a double integral here by the end of this video, and I'm going to walk through these things in order. So first I'll show you how you take a hexagon and put it in the floor. Then I'll show you how you build the deviation from quota function. I'll show you the integral, divide by the area, and then we're done. So before showing you these steps in order, let me just say real quick that one thing to keep in mind is that we have assumed that the candidates are ordered from biggest to smallest. Other than that, though, you can take whichever hexagon you want to put in the floor. So when I show you the next slide with a picture of the region, it's just some arbitrary hexagon. But it does respect the ordering of candidates. Candidate 1 is assumed to be in the lead. Candidate 3 is assumed to be in last place. So you have to respect that assumption going in. Okay, so here's a hexagon. And notice it's a 4-3-1 hexagon. So candidate 1 is apportioned 4 delegates. Candidate 2, 3, and candidate 3 gets 1 delegate. So what I've shown you here is sort of a standard transformation, a standard way of taking this hexagon, which is living in 3 space again, right? There are triples here, right? There are 3 coordinates here for these points. So this point here is where candidate 1's quota is 3 2/3, candidate 2's quota is 2 2/3, and candidate 3's quota is 1 2/3, and so on, right? You have a triple of quotas. The way you take this hexagon and push it down to the floor, the math is kind of interesting, but I'm going to shove it under the rug. This is the standard transformation. So this point here becomes 0√3/3. And this point here where candidate 1 is owed 3 1/3, candidate 2 is owed 3 1/3, and candidate 3 is owed 1 1/3 becomes a half √3/6, and so on. So again, there's just like a linear transformation under the hood that's taking this hexagon that lives in 3 space, and it's literally just like pushing it down into the xy plane. And in the xy plane, a given point only has 2 coordinates, right? So we're taking something that used to have 3 coordinates and now only having 2 coordinates so that we can integrate over it using our normal double integral techniques. So when you read this, though, by the way, you should just read this point and this point as the same. So like at the point, a half √3/6, that just is the point where the quotas are like this. At the origin, that's where the quotas are 4-3-1 on the nose, the integer point, and so on, right? 4 1/3, 3 1/3, and 1/3, that's the same thing as 0, -√3/3. So again, these arrows, like maybe they should have 2 heads going both backwards and forwards. This point and this point up top, these are synonymous, okay? It's just that this ordered pair here is the xy plane equivalent of this point here that was living in 3 space. So again, you should read this point and this point as like synonyms. They are both encoding the same quota information. One of them just happens to live in 3 space where it started, and one has been pushed down to the floor. So now that we've seen how to take a hexagon and put it in the floor, what is the deviation from quota function for candidate 3? Okay, so to think about that, we first should think about, well, like, what would this function even look like? If we could think about its graph, what would that look like? And again, I have to think about this thing is living in the floor. So I'm thinking about having ordered pairs as inputs and then outputting deviation from quota. So if I fed 0 root 3 over 3 into this function, what would it output? If I fed in 0, 0, what would it output? We have to think about that. So we can actually see what the graph should be based on this observation here. If you draw any horizontal line through the hexagon, which as we've seen before corresponds to keeping candidate 3's quota fixed, I would point out that the deviation from quota doesn't change along that line. So in other words, like this horizontal line here, if I move left to right here, candidate 3's quota is 1 1/3. It's 1 1/3 at this point, it's 1 1/3 at this point, right? You can see. So it will be 1 1/3 in the in between, any point in between like this, left, right. Now candidate 1 and candidate 2, their quotas change as you move left to right, but candidate 3's is fixed. So all along this line, what is her deviation from quota? Well, the math says she is owed 1 1/3 delegates, but she only gets 1 delegate. She is shortchanged 1/3 of a delegate. So her deviation from quota along this entire line is negative 1/3. There's a mirror image horizontal line here where the math says she is owed 2/3 of a delegate, but she actually gets 1 delegate. So she is boosted by 1/3. So along this horizontal line here, the output of the deviation from quota function is 1/3. Okay, so now you just have to imagine, right? So for any horizontal line, the output is constant. The output lives at a constant height. And so here we have height, get rid of this. Here we have height of 1/3. Along this horizontal line here, her quota is 1 and she gets 1. So along this horizontal line here that cuts through the origin, the deviation from quota is 0. Then we sort of like steadily fall at the same rate down to negative 1/3 all the way down to negative 2/3, right? At this extremal point, she is owed 1 2/3, but she only gets 1. So what kind of picture would you draw if you had to draw that information? You would get a plane, is what you get. If your constant output along horizontal lines, so these heights are constant along these lines, you will get a plane. So to get the deviation from quota function itself, I really just need an equation of that plane. But as we saw in chapter 12, to get an equation of a plane, you need 3 points on the plane, with the caveat that they can't all be in a line. But generally speaking, to get an equation of a plane, you need 3 points on it. Now in chapter 12, we did all the nice math involved with this. Given 3 points, what do? We made some displacement vectors. We took a cross product. That was all nice. You know, it integrated some different material, right? Putting the cross product stuff with the vector stuff. That was all nice. Anyway, for now, though, we're not going to mess with that. We're just going to use a calculator. But let me just point out, there's chapter 12 here, getting an equation of a plane. So for us, we just need to think about what are 3 points on this plane. So I input an x, I input a y, and out comes, outputs, a deviation from quota. What points are like that? Well, here are 3 points. There are, of course, others you could use, but let's think about it. So at the origin, where's the origin again? It's right here. So that's synonymous with this point. This point, the integer point, the quotas are the same as the integers. So candidate 1's quota is 4, candidate 2's quota is 3, candidate 1's quota is 1 on the nose. And if her quota is 1 and she gets 1, then the deviation from quota is 0. She gets exactly what she deserves. On the other hand, at this point right here, she is owed 1 1/3, but she does not get 1 1/3. She gets 1. So again, she's been shortchanged by 1/3. And similarly at this point here, if you input a half and root 3 over 6, that's the same thing as considering this vector of quotas right here. And again, she's been shortchanged by 1/3. So here, these 3 points, these first 2 coordinates are inputs, 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 and then what comes out, the output, is the deviation from quota. So of course, I didn't have to use these 3 points. I could have also used like this point up top. If I'd use this point, 0 root 3 over 3, what would the output be? What would the deviation from quota be? Well, here she is owed 1 2/3, but she only receives 1. So you'd put a comma negative 2/3 here if you wanted to use this point. Down here, you would put a comma at the end of this, comma positive 2/3, because she's owed a third, but she gets a full 1. So she is boosted by 2/3. So these points here are not the only 3 points you could look at. You could pick any 3 points from this hexagon as long as you don't pick them in a line. So don't pick this point, this point, this point, okay? Because those 3 points don't determine a plane. They're collinear here and linearly dependent. You don't want that. But anyway, so given these 3 points, again, you could hit them with chapter 12, but we're not going to do that. You should go to, where is this? You should Google equation of plane given 3 points calculator. And there's a Wolfram Alpha widget where you can type in the 3 points. So I'll spare you the typing here. You can do this on your own. If you do that and just hit calculate, then it will just give you the equation of the plane. And it just spit out this to me. Z equals negative 1.1547y is what it told me. So here is the deviation from quota function. It isolates the Z for you, you know. So it turns out it doesn't depend on X, right? Interesting. Only depends on Y. So there's that plane. So going in order, we saw how to put this thing in the floor. I did it for you basically, right? But you have to be able to interpret what these inputs mean. Then you have to get the deviation from quota function by considering points on that plane. And it's always a plane, by the way. It doesn't matter Hamilton's method or not. The logic is the same, showing that it's a plane. Candidate 3's quota along a horizontal line can't change because her quota doesn't change along that line. So when you move to SUQ or NIE or whatever other method you care about, you still get a plane. So you still just need to be able to generate 3 points like this. You ask Wolfram Alpha what that plane is, and now, finally, you have to integrate that function over what you're hovering over. And before I do that, let me just show you a picture of what's happening here visually. Okay. So here is that hexagon. I wonder if I can zoom in without breaking it. Whoop. I shouldn't have tried doing that. Anyway, okay, so here we are, hovering over that hexagon. Let me put the, okay, which way? Like this. Okay, so here's the X, here's the Y. And now that plane, if I graph it, here it is, like that. That plane looks like this. That negative 1.1, whatever it was, Y, looks like this. Okay, so I'm going to chop this plane and just look at it only above that hexagon. So I'm just going to take the part of the plane that's hovering over that hexagon, restrict the domain to that hexagon. So if I look at it just from above, see I fill in that hexagon. Let me look at it from the side. Okay, so if I were to integrate this plane here over just this hexagon, I take the volume above and subtract the volume below. And notice it's symmetric. Right? The volume above is the same as the volume below. And why would that be? Why would it be symmetric? Well, because as we've already discussed, right? So down here at the bottom, this is her biggest boost. She is boosted by 2/3. And there's a mirror image point up here where she is punished by 2/3. And here cutting through the middle is where her quota is 1 and she gets 1. So the difference is 0. And you just sort of like work your way up from that peak steadily down to this valley. And everything is mirrored, right? So again, like this line here, she was boosted by 1/3. This line here at these corners, she was punished by a 1/3, so negative 1/3. So it's all symmetric. There's just as much volume above as below. So when we integrate, we should get 0. And by the way, if you look at any other candidates, deviation from quota, you're just going to take this picture here. This is from candidate 3's perspective. This is candidate 2's perspective. Right, so for candidate 2, it's just like that corner is the top and that corner is the bottom. So it's the same picture, it's just rotated by whatever, 60 degrees or something. So same idea, right? Volume above, volume below. So it's still up to you to get this plane in the project. And then here's candidate 1's plane. See, so it's the same plane, but again, just rotated. Same idea though. So if I put them all in there, that's not a great picture, but you see they're just all the same. Same idea, you know, you're just changing your perspective. So the equation for the plane will change, but the volume above, volume below idea will stay the same. So anyway, there's a picture of what's happening. Let me hop back over here. Okay, so when it comes to integrating, it's useful to know what these lines are. So this is root 3x plus root 3 over 3x plus root 3 over 3. This horizontal line where you start, x is negative 1/2, and so on. You can read all this, right? So if you're going to set up the integral, you have to chop this region into two pieces. You have to go from -1/2 to 0, and then from 0 to 1/2 because the upper and lower curves change at 0. So let me just show you that. So if I go from -1/2 to 0 on the x-axis, I'm bounded below by this line on the y and bounded above by this line on the y. So you can see those two equations like there and there. Integrate that plane. Add. Now if I go from 0 to 1/2, see the lower and upper bounds change based on these lines. So you do have to make this chop. So then you, or I guess me in this case, but you later, right, will just ask Symbolab or Wolfram what these integrals are. And it turns out that this integral plus this integral is 0. This over here was like the, what? So there's just as much volume under as there was above on this piece, if you remember that picture I showed you, right? So things are just going to cancel out. And you do have to divide by the area, but it turns out the area of the hexagon is irrelevant because you multiply it by 0. Okay, so that's how you calculate the delegate bias of a candidate. So for you, if you want to now do candidate 2, you go through the same process, but now these points will be different, giving you a different plane. So for example, like what would this be from candidate 2's perspective? So let's go back up to candidate 2. So right here, candidate 2 at this point is owed 2 1/3, but she gets 3. So she is boosted by 2/3. So you slot 2/3 in there for that candidate. But otherwise the logic is exactly the same. Ask Wolfram or Symbolab, I guess it was Wolfram I showed you, right, for this plane. This region doesn't change, right? The upper and lower bounds on these lines don't change. So all that changes in this integral is this and this. And again, ask Symbolab and see what you get. Once you get an answer, by the way, you should be able to interpret it. So that we got 0 here. What does 0 mean? It means that if you choose election outcomes at random over and over and over again, so billions upon billions of elections, then on average, candidate 3 receives precisely as many delegates as she is owed. So sometimes she receives more than her quota, sometimes she receives less, but the 0 means that it all averages out. So in the long run, her deviation from quota is 0. It's balanced, which means that according to this notion of bias anyway, candidate 3 is neither favored nor disfavored. And again, we could see that from this picture, right? So when things are above the plane, that's when she's doing well. When things are below the plane, that's when she's getting punished. You have negative stuff down here, right? And the punishment and the reward balance out. You can see from the picture, right? Now this won't always be the case. So let me show you, see if it'll open. Okay, so here's SUQ. It says take 2. Let's see about that. Just open it. Okay, so here's SUQ. So this is from candidate 2's perspective, I believe. And now notice everything is above the floor now. See? So when everything is above the floor, you're not going to get things balancing out to 0. This candidate's deviation from quota average will be positive, meaning that whichever candidate this is favored. Let me show you another one. This is candidate 1, I believe. So again, favored, right? Everything is positive. And then candidate 3, ooh, look at that. It's all beneath the floor. So we predict that this candidate will be punished, which we already knew in SUQ, candidate 3 was punished. And this integral we calculating this negative volume will tell us that. So again, that's up to you in the project to set up the integrals for that. Okay, so let me briefly wrap up with a couple final comments here. Oh yeah, so the first comment to make is that the first final comment to make is that the delegate biases, as I mentioned before, have to add up to 0. So your first thing to do in this project is to, for Hamilton's method, I've done candidate 3. You now need to do candidates 2 and 1 to give like a complete report on Hamilton's method. But since candidate 3 is done, after you've done candidate 2, you then know what candidate 1's bias is because it all has to sum to 0. So you always get the third candidate for free. Now in terms of the work you have to do, you basically have to mimic this analysis I did for every candidate for every method. Again, keeping in mind that once you have 2 candidates for a method, you're done. You get the third for free. But where was like the work here? The work was getting these 3 points for a given candidate. That took some conceptual analysis, right? and then setting up the integral and asking Symbolab for it. But setting up the integral, you took this plane information and then you had to integrate based on bounds from the picture. So this picture I'm just giving you. The other pictures for the other methods are here under Chapter 15 Project Materials. I've included an NIE region picture with these lines included, you know, and all the transformation stuff, right? So all the like sort of geometric work is here. You don't have to reinvent this yourself. So like for this region here, if you want to integrate over this region, it's kind of obnoxious. You have to go from -0.5 to -0.25, right? So pick up this piece. But then at -0.25, the bottom piece changes. So now you have to go from -0.25 to 0, because then at 0, the top piece changes. Then from 0 to 0.25. Then finally, you can go from 0.25 all the way over to 0.75, it looks like, right? Because here the bottom curve and the top curve don't change. So this region actually has to be chopped into 4 pieces. Chop there, chop there, chop there, to give you your 4 pieces. So here you have 4 integrals. But again, the integrand doesn't change. So you just have to ask Symbolab for those 4 integrals separately, add them all up, and then divide by the area in the end, and then interpret your number like I did here. Okay, so I wish we could do this all in person. It's it's just easier to do it in person to explain all this and see what questions you have, right? So if you have any questions on anything, of course, you have a full week and a day, maybe 4 class days to get this done. So please reach out to me if any of this didn't make any sense, and I'll be happy to help you with it.